Hello guys, it's a pre-lab for today's and tomorrow's session because we accomplished all the measurements, we did the mapping of all shapes, and now we're supposed to do the math, calculate the electric field map. And from FIS 207, probably you know that there is very neat relation between the electric potential and electric field. Electric potential is a scalar field, electric field is a vector field, and the relation is as follows. It's a so-called gradient, minus gradient of the electric field, and very often it's used nabla symbol, the kind of inverse delta. Sometimes it's called del. It means that it's minus nabla v. What it means? Nabla operator is like partial differentials of each direction, I mean x, y, z, and it's produce vector. It means that when you use for the v operator on v, which is electric potential, you will end up with component x dv dx, component y dv and y, and component z dv dz. In our case, we deal with the only two-dimensional maps of electric field. It means that we deal only with dv dx, dv dy, and we ended up with the something which resembles very big array of numbers. And now the electric field map we have to convert to vector map, and to do this we will do it numerically. I mean, you know definition of derivative, and when you know in limit of h going to 0 you have like mathematical derivative, but in numerics, for example, the step size that we had constant step size because we had like limited time to do the mapping, and we limit the precision of mapping by making steps roughly in most cases it's about 5 millimeters. And how to calculate the derivative in Excel among the numerical values? You have to take the like difference of this between 2 points. In our case, like let's say cell A2 minus A1, and in x direction we just going like from A2 to A1. It means that from this value we subtract this value, we going along bottom. And in fact, this minus in the definition of gradients, we can just swap the cells A1, it means first minus second divided by step size. In y direction, we just deal with these two cells. We subtract from the first one, the second one in, let's say, y direction, yes? Okay, and that's it. If it comes to theory, I will just do the practical part in the next step. Okay. Hello. Now I will start the calculation of map of electric field out of the map of the potential, the scalar map, and I will start with the first map. It is dipole, 2-point charges, and maximum potential in the charge is 10 volts, goes gradually to the 0 in here. And we can notice that there are kind of circular equipotential lines, and in the middle is like smooth linear transition. And now we calculate electric fields. I'll start with Excel file. It's worth of converting into Excel file, but in fact here this is a special case that you can deal with CSV files, and it still will be okay, but I prefer to convert it. And now let's check what is the size of the array. It's 34 on 34. Let's check it. Yes, it's 34 on 34. This is because I set in the run volt scan 34 steps by 5 millimeters each step. But if someone extended the range in the script, in case of larger shapes, has to take this into account also, that it will be different value. Okay, now let's first calculate the electric field in this direction, in the x direction, by taking 1000 times A2, because we start from 2, because in the first is the caption of the step size, minus A3. And now I explain why 1000, because our step is in millimeters. It's 5 millimeters. 5 10 to minus 3 in denominator becomes the 10 to 3. It means 1000 in denominator. This is why. Even you can substitute value 200 instead of 1000 divided by 5. But now it's okay, because computer will calculate it correctly. And because the size of the array, I will explain later why has to be with dimension n minus 1. It means in our case 33, because both arrays in x direction and y direction has to have the same size, and it's not possible without truncation of the one row or one column in each of the dimensions. And now from 40 I need to have 33 of the rows, and to do this I need to take all and drag to the, and I said about the size, it should be one dimension less, 33, not 34. Always smaller by one from the original one. You have to remember this. The calculation in fact gave me the extra column, but in case of the y data it will not, and it will not give me the row data in 34. I will show you why. And now let's drag it to from 40 to 72. It will be 33. Okay, what if I would decide to have 34? Sorry, I calculated one more. Let's check. You would subtract some zeros from the last value, which would be not good. Yes, this is why we have to limit it to 33 rows. And columns 33, because another one will have only 33 columns. And this is the x. And let's produce y. Y will have so slightly different formula. It's equals 1000 times A2 minus B2, because we're going right hand side cell, because we go with the, okay, corrected, perfect. And now the same story. Okay, 33 on, why not 34? Because if you tried 34 you would end up with, sorry, my bad, very common mistake that could to happen, that I will make you aware of this, because when you deal with small monitor, everything is so large that you can end up not in the proper beginning. It means let's copy this. Okay, let's type it. It will be faster. 1000 times A2 minus P2 divided by 5. Okay, and let's make it until this point. It always has to be smaller. Sorry, this is previous one which was already smaller. It means that they both have to be equal. And it should produce me 34 on 30, 32. What's going on? Oh, still bad. I'll double check. A2 minus B2, correct now. And smaller by 1, it will produce a column with the size of, because I moved, I need to have extra data. Okay, and now it's correct. 33 on in the 33 columns. Uh, why not 34? Because if I would have 34, I will end up with the similar case like previously, that I subtract something that doesn't exist. It will be wrong. Okay, having now correct uh, row, I need to extend it to 112. 112. One moment. Okay, perfect. And let's double check the size. It should be 33 on 33. Sorry, 32. Okay, one more. Because with small screen it happens often. 33, yes, correct. 33. Perfect. Okay. And this was my Y data. And now very important step. We need to copy this. We need to in fact export this to separate CSV file. Control C. And the only way to do this is by making the new file empty and paste values. This is special mode of pasting, not Control V. Control V will like produce errors. Past values. Okay. And now we need to save it to the separate file. Type of the file has to be CSV, comma delimited, because our script for plotting will accept only this kind of files. EX CSV. Okay, I got the separate file. Let's close it. This is X, and let's copy the same guy, but for Y. Something wrong with the size, of course. Very common mistake. Control C, new file, this. And we'll pass it as values here and save as CSV file. Not this guy, this. Um, I will save it. Okay, and I produced two files, and now I need to use mob exterm, log into the, as usual, SSH, go to your folder, which is engineering 217, then 50, let's say 3 or 4, and then it's plotting folder. In plotting folder, we have two scripts. It's worth of checking this to follow with the copy panel to these folders, or manually, then you will need to manually enter to the folder. And in this folder is interesting script, vector plotter Python. And to launch this script, before launching, we need to copy these two files to the Jetson. Perfect, so I've got them. And now let's run the script, Python 3 vector plotter. And script asks us about file name of the X component. And here it will be not mistake. We should supposed to provide Y file, because our table is oriented that X is down and Y is in the right direction. And to make the proper vector fields, we need to first specify file 1A, 1EY. For the second X. Okay. Log scale. No need for log scale. And what it produce, let's say dipole, the name of output file. And it produce here the file, and I've got dipole vector plot PNG, and I double click it. what I'm seeing the vector map, the arrows vectors, and this was positive, and lines should be from positive charge to negative, and sign of arrows agrees. Okay, it's very hard to see the circular symmetry here because we are limited to the number of points and so on. But at least we tried the best, and we can see some physics here. Let's see, like how the electric lines are directed. And what you need to do exactly the same thing for all other maps. For all other maps, like my second one is the pointy one, and exactly the same. Make the file names correctly because you have to distinguish them in the very end in the report. Next to the potential scan, you will put the map of the vectors of the electric fields. Okay, and that's it if it comes to data. And then I will maybe give you some hint how to interpret it, how what it looks like in theory. Okay, in the next step. Okay, in theory, I do calculation of the electric potential and then electric fields in Mathematica using final uh, electric mode, final method, final elements method calculations. Okay, and this is the what we should get in theory from mapping of the electric field by making our steps like going to small to infinity almost. And this is what I noticed in the maps, previous map that I experimental maps, that some kind of symmetry here, circular and smooth gradient from max to minimum, from 10 volts to 0. And electric fields plotted, it's just the electric field lines connecting from the positive potential to negative and some kind of symmetry as follows. Okay, and for the another one, the shape as follows. What we should get this kind of distribution of the potential, because it was positive those guy, this shape was negative, and eventually the electric field lines are pretty complicated. Should in this area we should have some radial only lines, but due to the fact that this is huge in comparison to this one, the lines are slightly different. Probably the author of the experiment was meant to have these radial lines and maybe over looked the situation what happens here, because in total situation is as follows. But I will happy if we will see that we see some radial lines in your maps and direction will agree. In discussion you can think about what to write, but the hint is that from simulation we see that the situation is more complex than someone would think on the very beginning. Let's move to the next one. In the next one we have such a shape, such a potential. In fact, even though we have very pointy area here, we should get the highest gradient of the field. But in fact, in comparison to this sides and area of these sides, this is not as severe as someone would expect on very beginning. We'll see on the next field, because it's like parallel plate capacitor most likely, and in very pointy shape we have like more lines towards this direction. Yes, this is what says that also pointy points are here, and we see the same situation that the gradient is the highest. This is probably what author of the experiment wanted to convey and give you insight in for this experiment, for this shape. Okay, and the last one is this guy. And what theory says, interesting, which is real fact that inside we have shielded area and you should get the zero potential. But in your case, in experiment case, it was like not real situation because we want to mimic the situation of electric field in space by using electric conductive paper, and because the area was connected and this paper was conducting, and we got like equipotential like red inside. Yes, don't expect this situation. But in situation, if it would be some free space without the conductive paper, but in free space it's hard to measure the electric potential. You need very sensitive probe, extremely sensitive probe, and and this is the situation. This is why it looks different, and because we have paper and symmetry of the potential, equipotential line, something like this, and vectors like very similar to the parallel capacitor. From any shape in side of the flat, you should have lines perpendicular to the surface. This theory says always from the round, some kind of along radial, yes, somehow and more. And here we have fringing fields, and that's it.